All right. Good morning, good afternoon, good evening, wherever you are. I am Nick Chase, and I'm here to welcome you to today's webinar, Democratizing Connectivity with a Containerized Network Function Running on a Kubernetes-Based Edge Platform. Next slide, please. All right, so let me take a minute to introduce our presenters, or rather to have them introduce themselves. Magna, tell us a little bit about yourself.
Sure, thanks, Nick. My name is Magna Sahasrabuddhe. I'm a product manager lead at Facebook Connectivity. And the mission of Facebook Connectivity is really to bring more people online to a faster internet. Thank you.
Okay, awesome. Thank you. All right, and Boris, tell us a little about yourself.
I'm Boris Ransky, co-founder and chief marketing officer at Mirantis. For the context of this webcast, I've also been working very closely with Facebook Connectivity on our joint initiatives.
All right, wonderful. Thank you. Next slide, please. All right, so before we get started, a little bit of housekeeping. You will notice that there is a panel, usually on the right-hand side of your screen, and there is an option for you to ask questions. Please go ahead and ask your questions at any time during the webinar. Drop them in there. We will collect them and hold them until the end. Because I am psychic, I will answer the most common question right now, which is, yes, you will get a download of the slides when this thing is over, and also have access to the recordings. So let's just go ahead and move on to the agenda. And Boris, you want to give us a rundown on what we're going to cover today?
Yes, thanks, Nick. So we have several parts to the webcast today. We'll start with an overview of Mirantis Cloud Platform for Edge. We'll hand over to Magna to talk a little bit about what Magma is and what are the Magma use cases. Then we'll bring the two topics together by explaining the specific use case that we've been working on integrating Magma with MCP Edge for. And we'll go into the details of the integration, and then finally we'll close with about a 10-minute demo to actually show you firsthand what this whole thing looks like. So let's go ahead and get started with the first section. I know that some of you that may be familiar with Mirantis already know what Mirantis Cloud Platform is, but for those that are not, I wanted to spend a few minutes explaining at high level. So Mirantis Cloud Platform is our core product, which is basically an on-prem cloud infrastructure. And as much as 70% of our customers are actually in the telco space that use it for the NFV use case. The MCP consists of three core components as we visualize them here. The two that are probably most important is drivetrain and stacklight, and these are the two that we spend most of our R&D efforts on. Drivetrain is responsible for basically lifecycle management of the cloud infrastructure, where stacklight is responsible for monitoring, and the two work in conjunction with each other to ensure that the on-prem infrastructure that we deliver actually functions with high SLA, and whenever we do an update, the customer has a seamless experience. So if we were to zoom in a little bit further onto what MCP looks like, and specifically drivetrain and stacklight, it's basically a whole bunch of best of breed open source, mostly Apache 2 components weaved together. So drivetrain essentially is a combination of things like Git, Gerrit, Jenkins, Reclass, and Salt, which is a combination of tools that we use to basically push the updates into the cloud fabric. And stacklight consists of things like Prometheus, Kibana, Grafana, and a number of others that basically has a bunch of agents deployed throughout the cloud infrastructure and enables us to kind of view what's happening at the infrastructure level. Stacklight and Drivetrain, as I mentioned, they work together. Oftentimes, Stacklight may trigger something within Drivetrain to perform some operation, such as, for example, roll back some update if things are not working properly. So very early in kind of evolution of MCP, we realized that the core problem to solve is that of day two operations. In plain speak, that means that it's pretty easy to go ahead and deploy the cloud infrastructure, but it's much harder to continuously update and upgrade it such that the end users don't experience any disruption. So we've made it kind of a core focus of our company. As I've mentioned, Drivetrain is this magic tool that enables us to lifecycle the infrastructure. And effectively, you can think of it as kind of two main components. One is configuration. So we define the model of a cluster in a very fine-grained fashion for each of the clusters, starting with literally like the bare metal configuration all the way up to the version of the operating system, the higher level services that would run on the operating system, version of Kubernetes, version of OpenStack, etc. All is coded as a YAML file that is stored in Git. And then there is a Jenkins pipeline that codifies the change management workflow for a particular customer. So if there's a certain process that you would have to go through in terms of validating a particular update or change in the stack, that is codified in the form of various stages in the Jenkins pipeline. And the idea is that you have the separation between the cluster model that is stored as code in Git and the workflow that is stored in pipelines in Jenkins. And whenever you trigger a change in Git, it will automatically trigger for Jenkins to run through the pipeline according to the change management process that's codified there and make an update. So now moving, I guess, to the main part, and that is, what is this infrastructure that will lifecycle in the center? So the way that we deliver cloud to our customers is we do it in a kind of a form of this, what we call internally tuned stacks. And tuned stacks you can think of as kind of a pre-configured, predefined footprints of either Kubernetes or OpenStack or both, and some of the adjacent projects that would be responsible for networking and storage. And obviously, it's impossible to effectively lifecycle an indefinite number of tuned stacks, but we have roughly, I think, 7 or so that we typically deploy that effectively are kind of the core offering of the company. And one of these tuned stacks is something that we refer to as the Edge tuned stack. For each of the tuned stacks, typically there is a particular set of requirements that we try to cater to. So for Edge, and when we're talking about Edge here, I just wanted to go ahead and specify a little bit more what I mean by Edge, because Edge is a very broad concept. So here we're talking about effectively a network edge or a service provider edge, or in plain speak, it is a rack that a service provider would run somewhere in a regional POP. It's not a device edge. It's not something that would go ahead and just sit on the tower. It's one hop away from that. So the requirements for the network edge that we've uncovered through the engagement with many customers in the telco space, threefold. First is high availability. So you need to make sure that all of the infrastructure level services are highly available. 2 is workload diversity, and by that I mean is you would normally have a combination of VNFs and maybe MEC applications running at the network edge, and you will see kind of a good example of why workload diversity is important in what we'll talk about with Magma later. But again, in plain speak, that means that the edge, the network edge, is supposed to have a capability to support VMs, containers, and bare metal. So ideally, you would have single API for which you can actually instantiate virtual machines or containers, or in some instances, just have control over the physical bare metal nodes. And finally, because it is edge after all, you have to have a fairly small footprint. And again, small is kind of a stretchy concept, but when we talk about service provider edge, we cater to footprints between 3 to 30 physical nodes. So let's take a peek at what the actual edge architecture looks like. So the minimum configuration for edge is 3 nodes, or 3 controller nodes and 1 worker node, which you may or may not need depending on what you're deploying. But the 3 is the absolute minimum. The 3 nodes in MCP Edge effectively run Kubernetes API, so Kubernetes control plane services. The way it's done is, there's 3 nodes. There is a virtual IP manager sitting in front of an HA proxy load balancer. There is etcd database that is deployed across all 3 nodes, and there is an instance of a Kubernetes API server. And the idea is that you have a quorum here, and if any of the nodes fails, you still have the other 2, and you will not lose any of the functionality. And of course, as is the case with all tuned stacks in MCP, MCP Edge is lifecycled using drivetrain and Stacklight. One thing that I wanted to also point your attention to here is that for MCP Edge, we don't use OpenStack. So this is a pure Kubernetes on bare metal type deployment. The reason we do it for this particular use case is that there is a number of network functions or MEC workloads that simply do not require OpenStack. They may require VMs, and we'll go into that in a bit more detail later, but you don't necessarily need OpenStack in all its glory. You may need OpenStack in some cases where, for example, you'd want a higher level Mano system that is only capable of talking to OpenStack northbound APIs. But in this particular case, as you will explain it later, and you will see, we do not need it. So to make things more efficient and to make things more robust, we eliminated OpenStack altogether, and this is just a pure Kubernetes on bare metal install. So the final piece of our MCP Edge architecture I wanted to touch on before I hand over to Magma to talk more about Magma is Virtlet. So Virtlet is something that helps us to solve for this workload diversity requirement that I talked about earlier. And it enables us to run virtual machines using pure Kubernetes APIs. So there is a number of VM runners that are available out there for Kubernetes. Virtlet is unique in that it's actually implemented as a CRI, container runtime interface, as opposed to a CRD, like a custom resource definition, which, for example, KubeVirt is implemented as. And there is a number of advantages that you get with the CRI approach to a VM runner implementation versus a CRD. There's obviously pluses and minuses to everything, but again, we'll go over a little bit in more concrete detail over those advantages when we talk about the use case. I will save it for later slides. But the way that Virtlet works and some of the core components that I think it's important to understand is, again, it's basically CRI, just like Docker or Containerd or Rocket that kubelet interfaces into. One of the kind of a cool features with Virtlet is that when you run Virtlet, you don't necessarily need to have just VMs or just one CRI. So typically, natively with Kubernetes, kubelet would talk to just a single container runtime, such as just Docker or just Rocket or just Containerd. Virtlet implements a service called the CRI proxy, which kubelet talks to, which based on what the kubelet command is, automatically determines whether or not it should be passed on to like a container runtime like Docker, or if a request should be passed to Virtlet for provisioning a VM. And this is kind of a cool and important and somewhat unique feature of Virtlet that is also quite relevant for the context that we're going to explain later in running Magma. So I'll pause here and hand over to Magna to talk a little bit about what Magma does and what Magma architecture is. So Magna, over to you.
Thank you, Boris. Next slide, please. Yeah, so Magma is an open source software offered by Facebook, which is a distributed and extendable packet core plus converged access software. And one of the reasons why we built Magma is because, as I mentioned in my introduction, Facebook connectivity is looking to extend connectivity to people who today are either unconnected or in the underconnected parts of the world. And there are use cases there and deployments there that are not served well with the existing solutions. Either those solutions are not cost effective, or those solutions don't have the right footprint, the right deployment models. And so this is the reason why we built Magma. It's a software-only solution. It is built very modular and flexible, so that any operator, any service provider can start small with Magma, and as the network grows, they can grow the deployment. But just because it's built very flexible and it's built software only, does not mean that it is not built carrier grade. So we've absolutely built the software to be very much carrier grade, because those are the needs even in the markets that we are serving. As I mentioned, it's a pure open source play. We open sourced Magma earlier this year at MWC 2019, and it offers multiple deployment models. So I'll talk a little bit about what I mean in the next slide. Excuse me. So as I mentioned, the intent of developing this software was to enable network operators to deploy connectivity in areas that are not well served today. And this goes back to the idea that the existing solutions, from incumbent vendors, they are not necessarily built for those use cases or those deployments. And this is definitely true from a cost standpoint, but it is also true from the kind of footprint that you see. And this is relates to what Boris just spoke about. We want to be able to enable a core, a converged core, but very much in an edge model. And so hence the need for it to be running in a VM and running on a smaller footprint. The other thing that we've done with Magma is the whole built it truly cloud native. So the whole notion of being able to manage the distributed instances of Magma through the cloud, and the remote manageability is something that in the markets that we serve is something that service providers are looking for, because that ease of operations and that lower cost of operations is also something that the service providers in these markets are looking for. And then, of course, as soon as you have a truly cloud-native software, you also want to be able to enable, faster upgrades, the CI/CD kind of tool chains to support even telco software, while not distracting or maintain the stability of the existing core network that an operator has. And so the whole DevOps mindset is what we want to bring to the open source, thinking that's already, and the virtualization thinking that's already going on in the telco market. Next slide, please. So who is the target audience, right? And it is, if I have to talk about a few use cases where Magma fits very well, and some of the use cases that we are actually running in production right now. We work a lot with rural operators, and these are rural infrastructure operators who want to partner with the tier 1 MNOs, and they want to extend connectivity into rural areas. The way this works is because Magma is built so modular, the rural operator can run Magma on their in their network, which is sort of the edge for the MNO, and the Magma still allows the MNO, the tier 1 MNO, to be able to authenticate their subscriber and charge the subscriber and really extend that connectivity out to their subscribers. So this is one of the main use cases for Magma. In addition, with the advent of CBRS, now we are also looking at that space for providing fixed wireless access, as well as private LTE kinds of use cases in the US. At the same time, one of the more interesting use cases, and something that Boris will talk about a little bit more, is the use of Wi-Fi. This again, in some of the emerging markets, the as you know, the spectrum is highly constrained, and the operators there are really looking for capacity augmentation as well as congestion reduction by use of Wi-Fi. And that is possible by using Magma, because Magma is a converged access for LTE as well as Wi-Fi, at the same time providing the backend integration and connection to the operator's core network. And Magma, because of the way it's built, is also very suitable to drop new services and new applications at the edge of the network. Next slide, please. So very quickly, how is Magma built? There are three major components in Magma. As I mentioned, this is all software only. So Magma can run on bare metal, it can run on VM. Obviously, to kind of leverage all the advantages, it's better to run Magma in a VM. And these are the three pieces here, right? The access gateway, we have this fancy terminology called access gateway, but it is actually just software. We're not talking about an appliance here. The access gateway is really the converged core / edge, if you will. It has the complete functionality of an EPC today, and we are looking to add functionality for 5G as well. It has an S gateway, P gateway, MME, AAA, all of that functionality built into it, right? So because of that, it can function as a complete EPC at the edge, which means that all the subscriber traffic can get not only authenticated, but can get policy enforcement, as well as charging function implemented at the edge. The second piece of Magma is Orchestrator, which is really the what makes it cloud native. And the Orchestrator performs two functions. One is that it is the configuration single source of truth, because as soon as you have a distributed packet core, as soon as you have multiple access gateways, you need one source of configuration, and that's the orchestrator. The other thing that the orchestrator does is that it is also the network monitoring and maintenance node. So it collects network statistics from all the access gateways and presents it on a single pane of glass, as well as can integrate northbound with other OSS, VSS, or even visualization tools that an operator wants to use. And then the third piece of this puzzle is the Federation Gateway. The Federation Gateway really is a piece of software that sits at the operator's core network, at the edge of the operator's core, and talks all of the 3GPP protocols into a legacy core. And so it talks S6A, GX, GY, and all the diameter application protocols. So with that, the Magma, again, the way the software is built, if an operator does not have a legacy core, then they don't need a federation gateway. They can use an access gateway and the orchestrator to just stand up a complete LTE service. But if there is an existing operator core and Magma needs to integrate with that, then with the addition of the federation gateway, that is enabled as well. And so just wait, I think I'm going to hand it back to Boris. But before I do that, because of the intent here to have a smaller footprint converged access everywhere and having it running in a VM is where we have perfect synergies between how Magma is built and what Mirantis offers. Back to you, Boris.
Thanks, Magna. Okay, so this section, before we move to the demo, I wanted to talk about the integration that we did between Magma and MCP Edge. And Magma, as you will see from later slides, is a good example of what a typical CNF or containerized network function looks like today. So before I dive into the architecture and all of its details, I wanted to spend a little bit of time on the use case, because the question is like, okay, that's great. You guys made Magma run on MCP Edge. Why does it matter? So the reason why it matters, and then what specifically we're solving for a number of customers that we're working on, is around the use case of LTE to Wi-Fi offload. So today you probably hear quite a bit of buzz around 5G and faster speed and all of the cool use cases that 5G would unlock for you. But most of the problems near term that you see in wireless networks revolve less so about the speed of connectivity and more about the reliability of connectivity. The problem is that the networks are simply too congested and there is not enough, oftentimes, spectrum available, or there's simply not enough node Bs placed on the towers. So oftentimes you would start downloading something, you would get to like 20%, and then it would stop for 30 seconds, and then it will resume. And this is kind of a good, first-hand experience of, what a congested network looks like. So one of the ways to solve for the congested network is to seamlessly offload the traffic over to some sort of different spectrum, such as, for instance, Wi-Fi. And the Wi-Fi coverage nowadays in places like Bay Area is everywhere, and it's up and coming quite a bit in developed countries as well. Historically, though, the problem with Wi-Fi offload has been that of a seamless experience. You can technically, go into your phone and you can manually find the Wi-Fi hotspot in your house and log in, or in the airport. But if you go out of range, immediately, it disconnects. And the handover between the wireless LTE network and the Wi-Fi network, or roaming between the Wi-Fi access points, is something that is just now being perfected. So for this use case that we're going to talk about, we're using Magma to address exactly that. It's about basically taking an existing wireless carrier that has an existing LTE core, and extending that LTE core with Magma to seamlessly federate between the Wi-Fi access points and the wireless network of the provider. Providing that seamless experience is key. Again, one of the advantages of Magma here is that Magma is open and has all kinds of open interfaces that you can integrate with. And because Wi-Fi ecosystem generally is fairly fragmented, you need to be able to integrate with different wireless access controllers and potentially different Wi-Fi providers. And because of the openness aspect, Magma actually enables you to do that. And finally, a good component of Magma is that related to kind of the business side of Wi-Fi offload, basically visualization that enables you to see which access points from what Wi-Fi providers you're using, slice and dice analytics on it, see how much data is offloaded to Wi-Fi versus LTE, etc. So speaking of again the seamless experience and what the typical use case with Magma Wi-Fi offload would look like, is you have an end user there, which is like a device that would be connecting to a network and will intelligently steer the connection between either Wi-Fi or the packet core. The mobile packet core that you see there in the picture, we assume is some existing legacy core that a service provider has. And then there is a carrier Wi-Fi packet core that is effectively implemented using Magma. And both the kind of a legacy core and the carrier Wi-Fi packet core all connect to the same exact backend. So same HSS, same PCRF. So from the standpoint of the user, it's seamless, and moreover, from the standpoint of the operator, you can actually have a single data plan for a user that spans across both the LTE network and the Wi-Fi network. So it's one single backend, one single user entity, but two networks that kind of working together in conjunction. So now kind of, what are the challenges with actually going ahead and dropping Magma on MCP Edge, and what is it that we did? So, the title of the webinar is has CNF, or Containerized Network Function, present in it. And when we talk about containerized network functions, I think if you look at the landscape of what's out there today, and Magma is no exception, what you would more normally see is kind of like a mixed workload network functions. So Magma, as Meghna has talked about, consists of 3 key services: the access gateway, the orchestrator, and the federation gateway. And the 3 services ideally require a different kind of a deployment packaging to run efficiently. So the access gateway and the federation gateway would run inside a VM. Access gateway in particular needs just like direct access to the kernel data path, and therefore requires its own VM. Whereas if you look at the orchestrator is really just a purely stateless cloud native application that can purely run all of the components of orchestrator, can run in containers. And this combination of VMs and containers is kind of a typical thing that most of the network functions, forward-looking progressive network functions, are evolving towards. And that is the kind of footprint that one needs to be able to care for with the edge infrastructure. So now I wanted to kind of zoom in a little bit and explain exactly what services run how across what pods, nodes, and etc. And in doing that, also touch on some of the immediate concrete benefits that Virtlet brings in this picture that I alluded to in the previous slides. So if we were to zoom into this Kubernetes cluster, that is MCP Edge, effectively this high availability Kubernetes cluster, you would have a picture kind of like this. And right now we'll just use, for simplicity, just 3 nodes, and we'll say that each node is its own pod. Although, in real world, you would have Kubernetes schedule multiple pods across multiple nodes, and node to pod kind of a relationship is not one-to-one, but for simplicity purposes, we're just kind of explaining it as, showing it as one-to-one here. So inside of the this cluster of 3 nodes, we have a MySQL service that is managed by Kubernetes, and we have 3 instances of MySQL for redundancy. All the stateful data that Magma actually has will be stored in this MySQL service. The interesting thing is how HA is implemented here. So we actually, MySQL instances are containerized and run inside of a Kubernetes pod and are deployed into Kubernetes using Helm. Specifically, we borrowed quite a bit of work that was done in the OpenStack Helm project to make that happen. Then going kind of a pod by pod, we in the first pod, we have the orchestrator service running. And the orchestrator service is just a pure containerized application. So we're using containerd for this as our container runtime interface. And Kubernetes is then responsible for basically scaling the orchestrator pods however you want. Basically, Kubernetes controller logic decides and provides the HA for the orchestrator. And again, orchestrator is, in this case, we built a Helm chart for the orchestrator that we just deploy into Kubernetes. And all of the scaling happens behind the scenes from the standpoint of other services that interface with the orchestrator. It exposes a single endpoint that everybody can talk to. Now, the second important service that is deployed is the Federation Gateway, because we're talking about Wi-Fi offload use case. We are integrating with the legacy core of the provider. So we need the Federation Gateway here. And the Federation Gateway actually runs in the VM. And Virtlet is what spawns and is responsible for the creation of the VM in which the Federation Gateway resides. Now, one thing that I want to kind of have you pay attention to is that as a single Kubernetes cluster with a single kind of endpoint for Kubernetes APIs, but you have a combination of pure containerd-based workload that is the orchestrator, and you also have the VM workload that is the Federation Gateway. So we have 2 under kind of a single Kubernetes controller that is enabled through the this proxy service that Virtlet implements. The other thing that I think is important to point out here, and this is again kind of a cool feature that Virtlet gives you out of the box, being kind of a CRI implementation, is the ability to attach multiple CNIs and have multiple network interfaces via multiple CNIs, which is also extremely relevant for this use case, because if you look at the Federation Gateway, it needs to talk to kind of 2 important endpoints. The first endpoint is the orchestrator service, which is running as a container app in a separate pod. And we use Calico network to actually facilitate the communication between the orchestrator containers and the Federation Gateway that is running inside the Virtlet. And the second important kind of a place where Federation Gateway needs to talk to is the legacy core. So ECRF and HSS and all of these functions that the legacy core houses, you need to be able to actually, have connectivity from the Virtlet VM pod over to the backend core, and that is facilitated through a bridge CNI. And now, as we move to the third node or the third pod, we have another VM with now 3 CNIs, and this is the carrier Wi-Fi access gateway, or it was this basically Wi-Fi packet core, as we referred to it in the previous slide. So again, this is a similar setup to the Federation gateway in that Virtlet spawns the VM in which the carrier Wi-Fi gateway, or CWAG as we refer to it, sits. And there is 3 network interfaces that go into that Virtlet pod. One is a Calico interface that talks to the orchestrator service. One is a bridge interface that actually talks to the wireless access controller, or WAC, of a particular Wi-Fi service provider. And the third is basically, this is like your path to the internet. This is, again, a bridge interface for which your data path packets will travel. So I will pause here and hand over to Chandra to go ahead and show you guys a quick demo of how this whole thing works. So Chandra, over to you.
So I will be driving the demo part from here. So in this demo, we will be seeing end-to-end flow for Wi-Fi offloading use case using Magma on top of MCP Edge Cloud. So in this, the demo will flow with initially deploying MySQL in HA, next deploying orchestrator in HA mode, and then going back and just deploying Federation Gateway as a VM on top of Kubernetes with the help of Virtlet. And then finally, we will be deploying carrier Wi-Fi access gateway as a VM, similar to Federation Gateway on top of Kubernetes with help of Virtlet. And then we will be pushing the configs to both the Federation Gateway and carrier Wi-Fi gateway, and then we will be connecting a hotspot from a mobile, and we'll be accessing in the internet. So this flow we are going to see in this demo. So we have an automation script which will do everything, like installing MySQL as the first part. So here, so MySQL we do install with Helm and the Helm controller. So this helps us to seamlessly do the data work, like upgrading the MySQL, or if you want to scale up or scale down, or if you want to configure your backups whenever you need. So everything, the data work will go with a seamless, with zero downtime. So that is the reason we prefer to go with Helm and Helm controllers here. So once the MySQL has been done, the next part will be orchestrator. So that will come up as soon as the pods of MariaDB has been up and running. So this will also create the user accounts database for Magma. So automatically that will be done, and then followed with orchestrator deployment. So this will deploy both orchestrator controller and also NMS, which is again a dashboard for Magma. So it will install both the same. It goes with the Helm part here. So we have Helm chat for both, and that will be taking care of that. So even here, that day one, day two work will be the same. Like if you want to scale up or scale down, you can do through Helm controller. And the next is with installing the Federation Gateway. You can see it here. Even that is done through Helm. And we push any bootstrapping or installation within the VM through Cloud Init. That will be done with help of Virtlet runtime, and we do use Cloud Init to run the bootstrapping scripts. And then next it's carrier Wi-Fi gateway. Even that will be the same as Federation Gateway. It runs on with help of Virtlet, and the bootstrapping scripts will be done through Cloud Init. So that Cloud Init scripts and the logs I will be showing in the next few minutes. So once the deployment is done, so you can next is that creating a user for orchestrator. So that also will be done through this automation script. So I created an admin user, and now we will see the pods running. So all the MariaDB, orchestrator, and Federation Gateway, Carrier Wi-Fi Gateway, all the pods are running right now on MCP Edge. Now we will be getting to the dashboard NMS, and we will try to create a network here. So there are two things here. So you can do any creation through NMS, or we can through API. So I will drive through both the parts. Like one is like creating one part from the dashboard. Other part I will go through API, and I will show you how exactly the both works. Instead, I'm logging to the NMS. As is the fresh deployment, it will ask you to create a network. I'm going to create a test network. So once network is there, we'll navigate to the gateways, and it's empty as we have not yet registered any gateways. So now we will be back, and we'll see that whether the gateways has been deployed successfully or not. So for that, I will be checking the logs. So if you see, all the Cloud Init scripts from Kubernetes logs, I can see that everything is success, and inside the VMs, the containers have been created successfully for that Federation Gateway and Carrier Wi-Fi Gateway. Now we will try to register the GIS, both Federation Gateway and Carrier Wi-Fi Gateway inside orchestrator. So for that, I'm trying to get the gateway ID, the hardware ID, and the challenging key. So this are being used to register in APIs in orchestrator. So I will do drive this through API, because already we have seen how we need to use NMS, Magma NMS. Now I will show you how we can register a gateway through API. So I just need to fetch the IDs. I need to provide my network ID, which already I created. And next, I need to provide the hardware ID, which I already fetched it from Federation Gateway. I just need to copy this and paste it here. And the challenging key also I need to pull it from the Federation Gateway. Copy this. And then paste it in the API. And then rename, so whatever name you want to name for this demo purpose, I will name it as FEG01. And then execute the API. So this should create a Federation Gateway in orchestrator. So we will check that how this looks like in NMS also. So we can see that it's a 200. So we are good, and we'll go back and check in NMS how it looks like here. Okay, so the Federation Gateway has been registered here. Similarly, we will be doing for Carrier Wi-Fi Gateway, but before that, we will try to push the configs to the Federation Gateway. So this config is where you where you push all your DREs for HSS or PCRFs or RAIDers, every configs. Everything you'll be pushing from this config. So this config will be having all this DRAs for HSS address, everything you will provide in this configs. So I already have copied everything. I'm going to paste it here. So I customized everything, whatever required for this demo. So, and then I will be executing this. So this should push the configs to Federation Gateway. So we got 201, so and it has been pushed. So now we will get back to the VM. We will log into Federation Gateway, and we will try to see how the containers are. If they are running, then we will just go back to the mobile and see whether we can able to access the internet and by latching to the Wi-Fi hotspot or not. So the services are up and running and there is no issues. And next I will be switching back to the demo. So I'm using, my SIM has been already whitelisted in HSS. So I can, using this particular SIM, I can latch to the hotspot, which will do the authentication to your existing core network. So I got a link from my provider. I will use that link. My app will ask me whether I need to add this profile or not. So my app will directly push the Wi-Fi profile to my mobile. Now I'm going to see whether it has been added or not. You can see it's directly added and it's directly connected, because here you can see that my app, the app behind the screens will do everything. Like it will latch me to the hotspot if it is nearby and available. If not, it will directly latch me to the LTE or 3G, whichever is available. So whichever the signal is strength is good, it will latch to that particular thing. If it is a Wi-Fi is good, then it will latch to my Wi-Fi. If it is your LTE is good, then it will get back to your LTE network. So I can see it's already directly latched and automatically to Wi-Fi. Then now I will go and check whether I can browse the internet or not. I was able to browse the internet. Let me see if we can browse any content. Yes, we can do that. So that's the demo from end to end. So we deployed Magma on top of MCP Edge, and then we browsed the internet where the SIM has been whitelisted on the core network.
Excellent. Thank you so much, Chandra. Okay, so we're coming up on the top of the hour, so let's just kind of jump in and see if we can get some of these questions answered. Okay, so let's see. It's not clear from the Magma architecture. Is the orchestrator solution shown here a centralized deployment for all other edge clouds, or each edge cloud uses 3 servers for the control plane?
I guess that can be a question for me, but anybody else can chime in. So each edge location would have a minimum of 3 servers for the control plane. So if you have 10 edge locations with, inside 10 edge locations, you have Magma instance running, then you would have, 10 edge locations with a minimum of 3 servers everywhere.
Gotcha. Okay. What about the resiliency of federation and orchestrator in case a particular node goes down? How are you handling node labels changes for other nodes, and which component handles that? Again,
I think I can answer. If I understand correctly, the question is how do you handle the resiliency for the orchestrator component of Magma? So the orchestrator component is basically, it's a Kubernetes pod, and Kubernetes and the entire orchestrator app is actually a stateless app. So it's probably the easiest one to manage the resilience for. So as long as your Kubernetes is running, which it should be, because it's running HA across at least 3 minimum nodes, then the Kubernetes controller will be responsible for scaling and maintaining the resilience of the orchestrator component of Magma.
Okay. All right, Magna. Why did you choose to open source this Magma project? Did you consider trying to sell it?
No, actually, we did not consider trying to sell it. The intent always was to open source it. We're not in the business of becoming a hardware or software vendor. And so by sharing our code, we're hoping to help the industry, move the industry towards giving them access, right? Giving them better solutions to deploy networks.
Okay. Does the orchestrator use some sort of etc framework for LCM functions of container VNFs?
I can try and answer that. And then I guess Magna, you can jump in. So
yes.
I don't think that there is a super established etc framework for what a containerized VNF should look like. There is, I guess, as close to a consensus as possible that's now emerging around what the kind of a container native or container, or CNF friendly NFVI layer should look like, and that's basically a, Kubernetes running on bare metal and then OpenStack and other stuff running on top of Helm charts. And there's a bunch of diagrams that Etsy and Cloud Native Foundation and basically like all of these bodies that dictate the OPNFV, that dictate the telco standards that have. That diagram looks very similar. But when it comes to the actual architecture of a VNF and containers, I don't think there's a very common like Etsy mandated standard for what it should look like.
Okay. Is Magna, I think this one's for you. Is Magma evolving to 5G SBA?
Yes, Magma is evolving to support 5G as well. So that's something that we are evaluating right now, and it's on our roadmap right now.
Okay. How does the client detect the degradation of service, and when it is time to fall back?
So there's two layers of kind of orchestration that's happening here. There's the orchestration that is done by the orchestrator component of Magma that effectively monitors the Magma components such as CWAGs or access gateways. And if some sort of degradation is, basically happening at that layer, the orchestrator is responsible for that. And then there is like an infrastructure level degradations. For example, if there's like a physical node that died, or some part of like a Virtlet service hung up, or something like this. Some things that are completely invisible to the orchestrator. That is managed by MCP Edge, and specifically by the Stacklight component. So Stacklight deploys monitoring probes for every single service that runs in MCP Edge. And it basically continuously reports anything that's wrong. And moreover, there's automatic triggers that are configured for like restarts and then some of the like redeploys that drivetrain is capable of executing to remediate proactively some of the problems at the infrastructure level.
All right, excellent. Well, that brings us to the end of our time. So I want to thank our panelists, Boris and Magna and Chandra, for joining us today. That was a lot of really great information. And of course, I want to thank all of you out there. I know you're very busy, and we appreciate you spending the time with us. And as always, our super producer, Michelle Yukura, thank you. We could not do this without you. So thank you all very much, and we will see you next time.